This. Two years. Oh, you want this?
Hey guys, how you doing? How are we all doing? Good. Like I said earlier, I want to thank you all for joining me on Sunday for my JavaScript class. I'm so glad to see each and every single one of you there. And if you missed it, you know who you are. All right? If you missed one person from this class showed up to the JavaScript session. One. Lonely. Huh? I know, but you know what? Still, guys, feelings matter. All right? All right? Have a little compassion. Have a heart. All right? It'd be hard, sure. All right, somebody gave you an extension. Maybe you should have rewarded that person.
I didn't know.
Well, Andrew.
I didn't know there's 5 here.
Oh, that was an extension. Should have left class early.
Didn't. I was there till 5.
Didn't you hear me say it was an extension?
Rebuttal that.
Didn't rebuttal. There's no rebuttal. Okay. So I'm sorry for those that had to rush that out on Saturday night. Sounds like everybody, most of us got it in. It's not too late. Still get it in for whatever it's worth. So we're gonna do algorithms today. Just kind of an introduction. Don't be too scared of it or anything. We're only going to do a couple different algorithms and kind of explain how they're used. We're going to touch on a few just real basic concepts today. So I don't want anybody to be too lost. It's actually going to be kind of a quick class. I'm going to let you guys work on your projects today as well. So we're going to use Node.js again. So we're going to get back to using Node for these examples we're going to do today. There's only going to be a few. But hopefully everybody still has it installed and able to get back to it. We're going to do a linear search algorithm today and a binary search algorithm today. We're going to actually do install benchmarking libraries that can kind of test how fast these algorithms are working. It's kind of fun. I'm going to briefly go over big O notation. That's unfortunately named. And the group, we're going to do a big group pop quiz. So that'll be fun for everybody too, I think. And then let's do project work. All right. Do you like my Al Gore rhythm? Take a look there. All right, so let's start off real quick and let's just talk about the basics. So who wants to answer what is an algorithm?
Set of instructions.
Set of instructions. Sure, right? That complete a task. That's a good way to put it. Anybody else? Recipe? Yeah. I like that too. Right. It could be just as simple as a recipe, right? How to make a peanut butter and jelly sandwich, right? Really easy. So what are some examples of common computer science algorithms? Anything with sword? Yeah, that's a big one, really important one, right? Anybody else? Search, yeah, sure, yeah, sure. Yeah, there's a ton. We've been using these all along throughout the class. We just haven't really realized it. You know, even our for loops and a lot of the projects and functions that we put together that handle certain procedures. These are all algorithms, right? So coming down to the tricky part of this is obviously a little leading, but how do we determine if one algorithm is better than another? Speed, right? Very good. So how do we determine speed?
Depends on what you're using the algorithm for.
Sure. Yeah.
Because there are some algorithms that are faster for some tasks, some algorithms that are faster for some others.
Definitely true. Yeah. So how do we determine the speed differences between two algorithms?
How do you find it?
Stopwatch? Yes. True. I mean, really quick stopwatch sometimes, like a fraction of a second.
Computer is set up so that
Yeah, true. True. And there are Windows machines in there, so that's pretty fair. Stopwatch or a sundial might be appropriate for a right. Well, we're going to use benchmarking software. So we're going to use a benchmarking library to determine how fast an algorithm is going. So we're going to use that library today with a linear algorithm, and I think we'll have fun. I actually prepared a few things for today. So let's talk about like a sorted linear. So here's how I'm going to do this. I want everybody to be involved. Okay. So I have two little class examples we're going to do today. So I want everybody to be involved. Okay. So I'm going to think of a number 1 through 100. Okay. And let's make this easy. We're going to do it sorted, right? I don't want to miss any numbers. And if I call on everybody and we just call it random numbers, we're going to do duplicates. We're not going to hit it, whatever. So let's do it in number. And the only way I think of do a sorted 1 through 100 is to do what? How do we sort numbers 1 through 100? If I was going to use the whole class. Anybody? Instead of everybody yelling out a random number 1 through 100, how would I do incrementally, right? So I'm going to start on this side of the room, right? And basically what you want to say is like, is your number 1, right? Is your number 2, is your number, that way we don't miss any numbers, right? You guys with me on this so far? Okay, so I'm thinking of a number and starting now.
Is your number 1?
No.
2.
No.
3.
No.
10.
No.
4.
No.
5.
No. Just say 6. Nope. No. Nope. Nope. Nope.
0.
No. Well, let's try to do them more because I'm not going to remember all this. Go ahead, Damashi. Nope.
13.
Nope. 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 Nope.
7.
Nope. 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 Yes. Yes, that's the number 22. See how efficient that was, guys? So that is how a sorted linear algorithm works, right? We'll go through numbers in order to determine the number, right? So if you're thinking about going through a dictionary, it's saying you want to find the word zebra, and you start on A, and you go to B, go to C, go to D, go to you guys with me on that? Okay. Pretty simple. So let's talk about this really quickly. So let's say I have an array of sorted numbers. Okay? Which is a nice array. So let's calculate the minimum and maximum of number of iterations it would take to find a random number. So let's just say I'm thinking of one of these numbers. right? Not saying you guys have to do an order, but out of a random determination, what would be the minimum tries it would take for you guys to find my number? One, right? I might have picked 168. Tim said 168. Done. My linear search is done, right? Work like that, right? That's how it works. What would be the maximum? Oh, hold on. 14, right? It's possible that I guess 137 and throughout the room we're like, boom, until we get to 147. We try everything until that, right? You guys are with me on that? So if we search in a linear fashion, it doesn't necessarily need to be sorted. That was just a good way to kind of do that last example, because the last example, I didn't want to miss any number. So we did it in a sorted way. It could have been done in any way where you guys were yelling out numbers from 1 to 100 until we got to my number. I was just using it as an example so it didn't miss anything. But in this, it wouldn't necessarily need to be in this order, right? There's no purpose to it being sorted. It just looks like that. Does that make sense, everybody? Okay. All right. So is everybody on page with this? It could take 1 time. It could take 14 times to figure out my number, right? All right. All right. So let's do this. You guys can create a for each loop in Node.
So when you say it's 14 times, it's because once you have picked up the number and cut there, it means that you eliminate that number as the one you're looking for.
Yes.
Because otherwise, it can be another number.
Oh, of course. Yeah, it's just finite. It's just 14
Yeah,
numbers.
exactly.
Right. Yeah. In this case, yeah. Yeah, we'll get more complicated. Yes. So what we're going to do is create an array of numbers. Right, I can select this out to you guys so you have the numbers, or if you want to create one, totally fine. Try to create as 14. And then we're going to have a random value. We're going to use this stuff. You guys can write this any way you want to, but what this will do is pull out a random index, right, from step. You guys can see what's going on. That's all it's doing. Right, so we're going to write a for loop that looks at each index of the array to see if it matches the random value, right? So we go through each one of them. If it does match a random value, then we'll just do a console log and return the value. Okay, you guys with me on how to do this? Just do a for loop. If you match the number, you've gotten it. You've done your linear search. You guys with me? Okay, I'll slack this out to you. I don't know if I made instruction for this, so I'll just slack out this. All right, so remember how Node works a little bit. We just need to create yourself a folder, a file, run Node, and whatever the file name is.
Yeah, the 400. Plus one. I see. Yeah, no, it'd be 1 in 14. It's 1 in 14. Yeah. Yes, that's one of those numbers.
So then you get.
You might be reading so if it happens to be one, next the
So start with one, so it's 34.
yeah.
That's a random number.
Your random number will be one of those numbers. Yes.
And
So
range is a random value. How's it going to be in there?
once you have that, let's say it's 34. Now you're doing the for loop, going through each one of them. Remember the for loop where this it would go, the first one it would go through and say 10. You say no, it's not 10. So is it?
Random value.
So then the next one goes, is it 34? Yeah. No, just a random. Yeah. No, it's coming from that.
That wasn't.
Oh, yeah. Oh, that'd be weird.
That doesn't make sense.
No,
Stuff.
that'd be super confusing. Yeah. No. I'm like, wait, what do you think? Yeah, no, you're right. Yeah. It didn't say that. It's probably arbitrary. Right. There. Oh, by the way, if you guys would have been in my JavaScript class, this for loop would have been a piece of cake, right, man? Or a piece of cake.
Really? Watch that. Watch this.
Oh, yeah, thank you. Okay, I'll just give you like 2 more minutes to wrap up.
How many minutes?
Try to sign up.
I think maybe email Katie.
All right, guys. How many were able to come up with a solution? Good, good. Yeah, good. About half you guys. I'll just walk through the solution super quick. It was probably easier than you thought. I wasn't trying to do anything tricky or anything. I put together a couple different examples here. I just want to make sure I get the right one. Okay. Yeah. So in my example, I just did the for loop. Just went through the entire length of stuff. If it was equal to the random value, I just said stuff equals to random value. If it didn't, then it does not equal to random value. So in this case, did you guys come up with something similar to that? You guys did? Okay. Cool. All right. So let me just do it real quick. What do we call this one? Did I call it simple? Yeah. All right. So yeah. Oh, excuse me. All right. So it went through the list. I just randomly looked for a number. So it pulled out 168 out of the number, and it found out the first index didn't equal it, the second one, the third one, so on and so forth, until it finally ran into it. And then obviously, I just kept going. I didn't stop the application or anything, kept running through it. So that's kind of an example of how linear search works. I rerun it, it'll pick up a different random number and just try to pull it back. All right, you guys with me on that? All right, cool. So just as like a point of reference, if I were to double the list of stuff here, right? If I was to double the number, what do you think that would do with the length of time that this would take to run? By how much? Double. And if I was to triple the size of numbers, what would it do? How much longer would it take? Basically, keeping in mind as a factor here. We are talking about a linear expression here, right? So if it's only two numbers, it's going to take x, right? If it's 3 or 4 numbers, it's going to take x times 2, right? But it's worst case. Yes, that's right. Right. But any increase in size implements that increase in the amount of time we have to wait for it to complete, right? Regardless of whether we stopped it or not, depending on however that works, right? Okay, so check out this. I want to show you guys this little visualization, and I will Slack this link out for you to later play with because I know all of you will want to. So here is an example of like 31 just random numbers, and this is a searching sorter list, right? So I'm going to do a linear search for the number 614. I'll hit linear search, and it's going to check each one of these. I'm going to speed this up a little bit, so it's going to be painful. There we go. That's how a linear search works. You guys with me on that, right? So if I was to pick another number, 490, right? It's checking each one, right? They happen to be sorted, but it's still checking each one until it gets the right number, right? So depending on how long the list of numbers would be depending on how long the algorithm would run. Now keep in mind this one's actually stopping when it reaches its point, so its actual time that it takes, the time complexity is totally undeterminate, right? We wouldn't be able to tell. It'd be basically 1 to 1 power big O, whatever we run into. Okay, cool. So how do we feel about that piece of it? We'll go into a tiny bit more detail. But basically, how do you guys feel about it? How do you guys feel? 5? It's a 5? It's 5, 5, 5? All right. Huh? 4? Mega 5? Dang. That's a 5 plus? You get like 5 to the n? Ah. All right, so let's dig into the next piece of this then. Okay, so we are going to determine precisely how long it takes to execute this code. We're going to use benchmark.js. I'm going to slack out some code for you guys, and you can test this on your own. But it's basically a practice of testing how long an algorithm actually takes to run, right? So executing a piece of code several times will get a picture of how it displays on average. So the code I'm going to slack out, I will just run through super quick so you guys can kind of understand what's going on. And then we'll dig a little bit more into the next type of search. So you guys will get a benchmark folder like this. Obviously, you'll want to uncompress it, decompress it, uncompress it. And it has a package file. And it'll have a dependency, a benchmark dependency in there. You don't have to worry about it, but you will have to run npm install, right? Just so you know, so you guys got that. Included in this is a shared folder, so don't change the structure of the file folder. The shared folder just simply takes a variable amount of array indexes, right? So all this is going to do is just generate an array filled with numbers, right? Whether it's 10, 22, or 11 billion, right? Like it'll take any of those numbers. Based upon that, we'll be able to run as a simple. Simple is what we did in class, so you can ignore that. I think what we'll work with in here is the linear search file. So I'll kind of walk through this when you guys get it, but you can see that I'm using the benchmark library and then that shared generate. I'm pulling out just 10 numbers, and then what we're going to get back, and like I said, I'll slide this out in a second. I want to ruin the fun, but all right. All right. So you'll get something back like this, right? Containing benchmark on average linear search took 6.5 seconds to complete, right?
Yeah.
Well, yeah, I don't know what e to the 9th is, but that just goes on for a while. Sure. Nano, sure. Yeah, Nano. Yeah, if you want to put a round on that, feel free, but yeah, otherwise, yeah. So, okay, I'll let you guys play with that, and then we'll dig into the next part. I want you to all to kind of go through that and experiment with it. I'll psych it out right now. Let me know if you have problems installing it or anything to that extent. Okay. Once you guys get that open, I do want to walk through a couple more things, but I want everybody to get a chance to open it up on their own so we can see what's going on.
Oh, I did set up some time. Well, that's all right. I set up some time for us to look into the bench NPM library, but we don't. I don't think it's necessary. Skip that for now.
All right, has everybody got that open into a folder they can use, read, and run from? Yes? Okay.
All right, so walking through, like I said, we're going to be using Benchmark, the library here. We call that in just a minute. I'll show you what that looks like. Generates, just generating a number. Generating a array here, so I'm just calling 10, an array with a length of 10. Same thing as before, we're determining a value based upon the length that's coming in. So it's going to pull up a random index, right? Return that as our random value, just like we did, but kind of to a little bigger extent, right? Then we're doing suite, which we're getting from the benchmark suite. Don't worry too much about the functionality of this. Basically, all of this is going to do is run the for loop that we did in itself in order for it to find the random value. So that function is part of that library. That'll help us run that and determine how long that's going to take to run. So on start is just another method that's available that says, what do you want to do on start? Begin the benchmark, on complete, give us a benchmark filter, whatever happens to that, and return whether it's successful or not, and probably the results. Oh, there it is. Yeah. So on average, the benchmark name, whatever we labeled it as, and then took benchmark stat mean, which just pulls out the average. There's other things we can pull out of that, but obviously average is what we're going for in this particular case. Runs the test. So it's just chained. I think you guys can see that. Bam. Don't have to worry too much about knowing how to do that or anything. Just outside of the exercise. So let's all do like, I'll put in a length of like a million. And then see what we get. If you run into a heap error, let me know. We'll work through that. So where we'd run this from is the solve benchmark, and the file that we want to run is just linear search on its own. Yep. Benchmark. Yep. So once in benchmark, I'll do the npm install. It'll install appropriate libraries from the JSON package, and then we can run the linear search. You guys with me on that? All right. Give it just a minute. Not working? Yeah, npm install, right? Can you remove this on your
Which one of the benchmark?
Fine, baby.
There we go.
Not good? Yes. Yeah. Yeah, that's a good.
New computer, I don't know if I had everything installed.
Did anybody else have any trouble on it? You good? You good, run? You good number? What's the number?
Not understanding.
And you ran how many numbers? Million? Oh, yeah. Really? Yeah. You did it right? All right. How many did you got? 1 0 0. 1 0 0? Okay. It changes every time. Okay. It changes every time, right?
Yeah, you probably won't be exact, right?
Okay. Me? 0 0 0 2. All right. Nice. Brady, what do you got? All right. Nicole, you get it run? .001. All right. Good.
So what if we did this? What if we added a few more zeros to it? Right. All right, maybe. Right. So if you do break it, and I hope you all do, because I'm prepared for that such eventuality. What I'm hoping to do is if you open up that README file, I have a little special code in there. All right. It'll give us just a little bit more time to run. So if you open up your README file and you ran into that heap size extended error, go ahead and throw that sucker whatever you want to, and you won't run out of it because it's looking at one manager space, right? I had 3 zeros. This is the mean, so it should go up still because the average will increase as the linear size of the expression.
What does no maximum
So that adds more memory to the heap, which we haven't really gotten much into, and don't worry too much about it. It just gives more memory to the operator. Yes. All right, so I'm gonna run out of time here. So, you guys want to go ahead and try that with a couple of zeros? You'll be stuck with that. So that'll be good there. Anybody try that? Are we all ready? I probably added too many zeros.
It's gonna happen. I'm just gonna wait for that in the background. Oh wait. Oh, I still got it. Still got it. You did? Oh, look at that. Out of heap memory, right?
So I could have added a few more onto that, right, just to get it. You got the same thing. So
Making space available to use.
allows us to do more with that, but the point isn't the amount of memory you're using it. We're just showing how that linear search algorithm works, right? And how that's being used and the time that it takes to run that.
You guys with me on that? All right. So, cool. Good.
So how could we improve that, right? So I'm just gonna dig a tiny bit into this. I promise. I kind of went even beyond the scope of what is suggested for this, but I want you guys to get a kind of a little bit of an understanding, right? The linear expression is this O of n. This the line that goes straight up bottom left to the top right. Right? It's just O of n. That's what we're dealing with, right? What we're going to be dealing with is the binary search next, which we're going to talk about.
That's the red one, right? That's the O of log n, right? So we're going to be getting into that next. Quadratic, the O of n squared, up here in purple, but that's not something we're going to deal with either. So really, right now, what we need to focus on is this middle one, the top left and top right, right? This amount of space and time, it goes out pretty evenly. As you grow your list, it expands as an equal distribution. You're ready, right? In some cases, in binary, it kind of levels off because of how that works. I'll totally get into that in a second. But time complexity is a function describing the amount of time algorithm takes to complete the amount of time. We won't be getting into space complexity today, but basically it's the amount of memory that an algorithm takes to complete the site. So you have this time and space algorithm. I don't want to lose anybody too far with that, but that is how conceptually it works. These are all just other O's, but it's considered, I don't know, technically an omega. I don't believe it's used in the same way, but big O notation. I do have some fun links that help describe all the different algorithms if you guys are interested. So I'll send that out later. All right. Any questions about that, guys?
Could you have algorithms that take into consideration the size of the data to pick and select the best algorithm, because each of them shows that there is a different point of the maximum.
Right. Well, that's up to you to determine the best algorithm to use in the application.
Otherwise, I was wondering if there is such a thing as a algorithm that will do that. So, meaning everything is pre-programmed inside, and then you count and select one.
No, I think we're getting kind of in the artificial intelligence realm of things, and I don't know if there's anything that would take a set of data and go, this is the best way to rigorously search through. I know, to answer your question. No, I'm not sure. All right, guys, are you guys ready for another exercise?
Complexity of your algorithm. Yeah. Sure, what we just did was linear.
Linear. Right. Straight up.
That's not so good. I mean, there are a bunch of them on there that were better than
Yes.
the one that gets better than
Yeah.
Constant's the best. The O of 1 is the best.
Well, let's do this one next. Let's do this one next. You guys ready? Big car clap. With me. I'm going to do a binary. All right. So I'm going to do that same demo that I did before, right? Except we're going to do it in a binary fashion. All right. So this time, feel free to yell out any number. All right. Yes. You yell out any number, and I'll work out how it works out. But generally, a binary search only works in an ordered fashion, a sorted fashion. So I don't want to mislead anybody. But let me set this up this way, and then we'll walk through how it works. Then everybody knows that. If you know I'm going with it, but hang on. Okay, so I'm thinking of a number, right? 1 through 100. Down, up, down, up. If you're paying attention. All right, if you guys know where we're at, it's between what two numbers? 60 and 75. That's where we're at. It's all right. Sorry.
70.
Sorry? Up.
72.
Right on. You guys see the difference between that and linear? Right? 5 guesses instead of 73 guesses to get there, right? And if we distribute it properly, it's either equal to or less than the amount of time it takes a linear. Obviously, generally less time it would take to do a linear algorithm, right? At least equal to the same time. Do you guys want to walk through that exercise again? In my mind, I thought it was going to be like a lot more. Yeah. Yeah. Binary. All right. Not so much. Good. That's fine. I like you guys anyway.
Okay, so let's do this. Let's do the binary search. So what you're going to do is you can take one of the algorithms or one of the samples that we had before. Actually, because with binary, you have to have a sorted list in order for this to make sense. You guys understand why? Do you? Great. It's kind of a tricky thing. So let's use that first example that we used in class today, that sample where we had a list of numbers. If you look at that list of numbers, they're all in order. They didn't need to be in order for linear, obviously, right? But for binary, they need to be in that way because I could say 10 more than you guys get it, right? We're breaking up, right? We're distributing among the, you know, how we're chopping up. So why don't you guys go ahead and try to use that first example and do a binary search, right? Try to take the list that you have and see how many times it takes you to get to a binary search using the less than, greater than, instead of equals. Remember, in the last one, the linear had equals, like you got to that number. This time, you get the number and determine whether it's less than or equal to. You guys kind of seeing what I'm doing here? And hopefully that'll get you to the right number. Oh, yeah, actually, and if you guys want to, or if you want to get a better understanding of it, just Google online binary search and you might be able to find some functions and stuff online. Go ahead and use that if you want to, otherwise just use it on your own if you want to. So feel free to Google it, do something to research it.
So, yeah. So people. Well,
You guys want a few more minutes?
Yeah.
Yeah. It's, you're actually not. Where this is part of subtraction.
Yeah.
I don't know why.
You want the other one?
Virginia Lindsay.
Just like run the value of the employee money.
All right, guys, a big power clap. All right. How many successfully did a binary search algorithm? Couple of us. Do you kind of get the point, or what conceptually what we needed to do, right? I do like the example of a dictionary, right? If I'm looking for dinosaur, I could go up with a bigger D. Yeah, looking up D, and I open up the book, I open up in the middle, I land on H. Am I going to go back or am I going to go forward, right? Makes sense, right? I'm going to go to the front half. I land on E. Am I going to go back or forward? Keep going. So it works like that, right? Does that kind of make sense, guys? So, and just in my example, and I'll slide this out for you too. I'm using a binary search function where I'm just supplying the a numbers array, and then just looking for a specific number, 77, and then determining how the application runs it, right? So obviously I could have just passed in a random number just like we did earlier. Either way would have worked in this condition, but the end goal would be just to return the index that worked, right? But simply enough, I was able to go through and say, okay, so while the max index, which is set up through here, the length of indexes, right? The complete length -1, 0, right? The min index is going to be 0. So the first time it goes through, it's going to take the entire piece, right? So while it's less than or equal to the max, is less than or equal to the min, eventually the min and max will get closer and closer together, right? Does that kind of make sense? So the current index being whatever it happens to be, right? The math floor of min plus max divided by 2, which is just max stab in the middle, right? And then it says, okay, the current element is whatever that happens to be. If the current element is less than the search element, then we'll go ahead and increment the index by 1. All right? So hopefully you guys are kind of, you didn't have to do it exactly this way. You could do it a different way. But I want you guys to at least conceptually be thinking of it. The purpose of this exercise in this class, today's class, isn't to necessarily code it, just to be able to understand it, see it, be able to use it, and maybe future on exercises you can use this kind of algorithms to speed up your code, right? If the current element is more than the search element, then do the same thing, right? It's more than what we're looking for. Look below that index, right? It means that we've got to 83 and we're looking for a 77, right? So we need to remove something, right? Otherwise, just going to return the actual index. That means we hit it. Otherwise, return false, which shouldn't happen. Okay, so I'll select that out for you guys to play with later if you want it. It's kind of fun. Kind of a cool thing to do. Uh-huh.
You guys do social interviews? I've seen that a lot. They're really popular job interview questions. They make you write out the algorithm.
Yeah, in fact, I have a link I'll slack out about that exactly, about job interview questions and how that kind of tests the algorithm. Because like I know Google's famous for having some where they're like, you know, if you're in this situation, how do you determine this in the shortest amount of steps or whatever?
So yeah, do you have any examples of any that you remember? Okay. Yeah, and they're just kind of like just trying to get your answer in the shortest amount of steps or in any amount of steps, right? So
That's the purpose of that exercise. So let's do a pop quiz. You guys ready for a pop quiz? Do you want to do this on your own or together?
together, or together, that happens first. Okay, could someone define algorithm? All right.
Recipe instructions? Yeah, and that would be like finding like a refinement to an algorithm, right? In a sense, but an algorithm itself is just steps to a solution, right? Just any steps. But yeah, you're right. Yeah, absolutely, right? Ooh, I did want to dig into one other thing back, but I'll keep going. Okay, so how might you choose objectively between two different algorithms? We had not necessarily just the algorithms we did today. But let's say we wanted to run two different functions and we wanted to find an objective way to determine which one ran faster. What would be a way to do that?
Okay, so you first you calculate the linear search, then you use area and where the curve was born.
Right, and if we're comparing like a linear and binary search, that'd be correct. Yeah. If we're just comparing any algorithms, what would be a good benchmark? Benchmark, right, would be a good way to compare two different algorithms. Right, which one's running faster? Right? Does that make sense, guys?
You guys all with me on that one?
Okay, so be on the test list. So what is the time complexity for an algorithm that takes twice as long if you double the size of its input, 3 times as long if you triple the size of its input? What is the time complexity for an algorithm? Which algorithm? Linear, right?
This guy's linear. All right. Okay, so
Why is binary search so fast? Why were we able to come up with the answer 72 within, what, 5 steps or whatever it was?
that is correct, right? Right. Sorry. Yeah. No, you're absolutely right.
Does everybody understand that? All right, we're having the iterations every time we go through it and going, here it is, here it is, here it is, done. Figure it out, right?
Is with me? Cool. All right, so
What is one essential difference between binary search and linear search? Obviously, there's many, but what's one?
essential search, something we didn't necessarily cover in this last part of the quiz. That's true. That's true, but right, I might have that as another answer to another question. But yeah, you're right. You're thinking correctly, right? What else might I be looking for?
I think it's too simple. Maybe the questions are a little bit misleading. What I'm looking for is just the time complexity, just faster. That's all.
That's all. Just faster. Okay, so what?
Steve, Mike, explain one way
we might use binary search in a sorted array, right? There's a sorted array, right? Or we have the option of sorting the array before we run the binary search, right?
What about when you can also go?
What might be, hey Pierre, what might be one reason we might opt for a linear search? Pierre, what might be one way we opt? What might be one way we opt to do a linear search?
When you can't sort.
Oh, okay, yeah, that's in mind.
So did everybody get that?
When we can't sort it, we might have to do a linear search, which we know is really slow. Huh? You guys with me on that? Cool. How we all feel about binary and linear search? Are we all experts, 55? that a 1 or a thumbs up? Okay. All right, good. Yeah. Are you guys okay over here? Good. Sweet. All right. So, do you guys want to do a fun algorithm project thing? All right. So, this was my work problem of the week. Not of the week. I have other problems during the week. This one was one I just had to solve over a lunch period, and it was once I solved it, it was fairly easy. But I want everybody to have a chance to look at it. Okay, so I'm going to explain it. Read what's up here, but I want to explain the situation, right? So I had a cron job, right, which is just like an automated build process in Jenkins, right? Within a cron calculator, cron timing, I can't specify whether or not it's a weekend or a business day, right? In a cron, you can only specify the days of the week, right, of the month. So, or the month, rather. So if I said the 1st of the month, 2nd of the month, 3rd of the month, 4th of the month, whichever, that's what I can specify within my cron job, okay? That's it. Okay. The goal of my application is to send an email once a month, first business day of the month, excluding holiday, right? So if the first business day was the 2nd, it sends. If the first day was a Tuesday, it would send. If it was a Friday, it would send, right? So what algorithms or steps could my application do to work properly, right? My application itself can determine business days of the week. I can determine whether it's a weekend. I can determine all that stuff within my application, obviously. It's really the limitation of the fact that cron can only send it X amount of days of the month. It doesn't know that it's a business day. My application does. So I solved this problem in just 2 conditions. I want to see what you guys can kind of come up with. I'm going to let you sit on it for a minute. I'm not going to just give you the answer.
If the 1st or 2nd, there is a Saturday or a Sunday. And if it's not the Saturday or Sunday, well, the 2nd and the 5th.
2nd and the 5th. There's no historical value. I don't know if I've sent it already. I don't know if I don't know. I'm not saving it in there. I can't look back and go, this was sent already. I don't have that feature. Thinking it out. This one come to. You guys understand the problem first of all? Is there any questions about the problem? Has to be a business day. Checking if done. Yeah. You definitely don't want it to be a Saturday or Sunday, right? Right.
I check for first of every month. It falls on a weekday. Sunday.
Yeah.
It falls on a weekend. I check to see what Friday also. Saturday, that day, and
I can't specify what day it is. Well, holidays are good. Holidays are good. Oh, holidays good. Yeah, but I can't say I'm going to send it's a Saturday. I'm going to send it on Monday. The cron job is just going to run first 3 days, first 4 days, first 5 days. But I just gave away part of the answer. Yes.
I look at the date, what day is the business day? Every month, and I check the day for the business. Well, I check to see if it's a business, and I check if the previous day was a business.
Okay, so
The first one.
So the cron job itself, let's just say with this programming problem. Now remember, I could just do with the cron, this is automated, it's chunking through. It's gonna say the 1st, 2nd, 3rd, 4th, it's just gonna go through. I could say, just do a limited amount of days. How many days do you guys think that would be limited? If I wanted to always pull, no, 3. All right, so let's start there, right? So we know for sure the cron job itself is just going to run the 1st, 2nd, 3rd because one of those better be a Monday. Or better be a business day, right? Better be, one of those better be, right? So whether it's a Friday, Saturday, you with me on this, somewhere? Okay, so let's just assume the cron job is running the first, second, third. Okay? You guys with me on this? All right, you guys want the solution or you want to talk it out?
Well, what about if you have a holiday that was Memorial Weekend?
Well, like holidays excluded. Holidays excluded.
So it only runs on the first, second, and third of the month.
Yep.
Oh.
Monday, you send it? All right, so let's I know you said, here's what I'm gonna do. I'm gonna just give the first part of it. You guys have already said it. So obviously, if it's running, as we know, it's running the first, second, third, right? If it's a Saturday, right? Sorry, am I writing, guys? Program. Or a Sunday, right? Then no email. Right? This is the first step that I have in here so far. Right? If it's a Saturday or Sunday, no email. Now it's running the first, second, third. So we know that for 100% fact. That's the first step. I have one more little condition that has a couple other things in it. Whether or not to know not to send an email or to send an email when the cron's running. Rob, you know it already. Brady, you know it already. Am I missing any other information that would help? Yeah. This will have just two conditions in it. It took me a lunch period to figure it out, so if you guys can't figure it out in 5 minutes, don't feel bad about it. What's that? Ooh, you're really, really close. You're on the right track. You're on the right track. He said, it's, I was gonna be less than 4 because of that, but you're thinking in the same vein. You guys, what? You just want it? Monday or Friday. Well, why would it matter if it's a Friday? All right. Okay. All right. You guys, it's not. This isn't super. Isn't super easy. Like I said, it took me a second, right? Okay. All right. Okay. So, if the day that we get right is over 1, right? Hold on. You guys with me so far? And what? And what? This is all we need. One more little thing. One more little thing. That's my ampersand. You see that? What was that? What am I looking for? Well, yeah, that one's not. That one it would never be greater than 3 because we're only setting the cron on first, second, third of the month. Well, that's true. But if this was only the case, we would send emails on. We'd never send an email on the second, third. All right. We don't want to do that necessarily. You're so there.
You want to keep going? You're like right on the edge. Wednesday? So what about Tuesday, Wednesday? That might have been a. I don't want to rerun the opera. I don't want to rerun it. All right, one more piece. All right. Oh, I'm sorry. Not good. All right, I'm just gonna put and day of week is not equal to Monday. You got that? That was fun. Let's walk through it. So if it's not Monday, Saturday, Sunday, that's easy, right? If a day is greater than 1 and it's not equal to a Monday, no, send an email, right? So meaning if it's a second or third and not on a Monday, there's no way I could have sent something out on the first and second, or even the second, or even the first, right? So in the condition that it's over 1, it better be a Monday. Otherwise, I would have already sent the email. You guys got it? Kind of a tricky one, a little bit. You guys got any questions about this, or do you walk through it? Yeah, go ahead. Yeah. The cron? Yeah. I can't with Jenkins. I can't say only days of the week. I can say day. I can say the day, but I can't say in Jenkins. I can only say the day of the month. I can't say that this is a business day. I know in some cron you can say like 1W or 2W, which actually means like a Monday or Tuesday or whatever. With Jenkins' job, all I can say is it's first, second, through 3. So I have 1 through 3. That's where my job's running. So it's 0, 2, comma, 1 through 3, comma, 0, comma, whatever. So it's going to run every month and only on the first 3 days. You guys got it? Or is that not too fun? Sort of fun? All right. I thought it'd be fun. All right. Good. Cool. All right. Well, we're here. Questions, guys? All right. Big power clap. All right. If you guys want to take a little break, you can, and then you can come back. And once you get together with your groups, we can do projects the rest of the day and work on that.